Hi class, today we are talking about section 4.3, quadratic functions and their properties. And quadratic functions are something that you should be very familiar with. We're just revisiting the topic to help us understand the properties of functions that were talked about in chapter 3 and applying them to quadratic functions and seeing how those properties are in play with a function that we're already very familiar with. Up here at the top of the page, I just wrote the quadratic functions in two different ways. On the left, I have it written in general form, where it has ax squared plus bx plus c. And then on the right hand side, I wrote it in vertex form, which is what we're going to be using more in this section. Now, we get from one to another by using completing the square, which is another skill that you have to practice. So we're going to get a lot of practice on some topics that we should already know. For the first one, for the first question, it says use transformations, and we did transformations in chapter 3. We're going to do them again right now, but notice that I have this graph technically written in general form. Now I want to take this and just rewrite it one time and say parentheses x squared plus 3. And why am I doing this? Well, I want to show that this modification is outside my parent function. Right? My parent function is x squared. And I should know what x squared looks like. But let's go ahead and just put it down here for reference. You're looking at a parabola with its vertex at the origin. Right? And then we have certain points like 1, 1, and 2, 4, and negative 1, 1, and negative 2, 4. So we know that it's going to go through all these 5 points. And when I transform it, I want to make sure it goes through all the same points. This is going to be the same as the vertical transformation, this plus 3. So that means I'm going to take my origin, and all of these points are going to move up 3. So I'm going to add 3 to all the y values. And so I'm going to go to 0, 3. And what was once at 1, 1 is now at 1, 4. And what was once at 2, 4 is now at 2, 7. Negative 1, 4. And then negative 2, 7. And so there we go. We've taken all of these 5 major points that are on the parent parabola. We moved all of those up 3 by adding 3 to the y value. And then do your best to connect them in a parabola shape. We're going to use the same steps to do number 2. However, we're going to have to do a few extra steps to get it into vertex form first. Question number 2 asks us to use transformations to graph the following. So we want it to be in vertex form so that we can graph it using transformations. However, it's not. It's in general form. So we're going to have to do some work on that. Let's go ahead and write that equation one more time. I notice it has a negative coefficient. You have to pay very close attention when we have negative coefficients. What I'm going to do to complete the square is subtract 2 from both sides. And also, at the same time, factor out that negative 2 coefficient out of what's left. So that's going to be x squared minus 3x. And give yourself some space to complete the square. Now, when we complete the square, we always want to look at that middle term after that first term has a coefficient of 1. And that middle term is negative 3. And we're going to divide it by 2 just by putting in a fraction over 2. If we can actually divide it, do that division. But if you can't divide it, leave it as a fraction. And then you're going to square it. So here we're going to get positive 9 over 4. So I'm going to add 9 over 4 on this side. Now, we have to be very careful about adding 9 over 4 because we can't change both sides of the equation. But notice that there's a coefficient here and then that 9 over 4. So we want to match that on the other side. So on the other side of the equation, I'm going to say minus 2 times 9 over 4. Let me just rewrite what I have here. I'm going to erase my work a little bit. I'm going to rewrite it as f of x minus 2 minus 9 over 2. And that's going to be equal to negative 2 x squared minus 3x plus 9/4. Alright, just want to point out that I added on the left side the exact same thing that I added on the right side. You want to make sure that that's equal when you add it, so you can't forget about that negative 2 coefficient. In order to simplify this, I have to think about my 2 over here as 4 over 2. Think of it as negative 4 over 2 minus 9 over 2. That's negative 13 over 2. So I'm just going to write it one more time. And I'm going to say f of x minus 13 over 2 is equal to negative 2 x minus 3/2. Do you remember that 3/2 from earlier? That was from taking that b term and dividing it by 2. And then we're going to add that 13 over 2 to both sides. So I'm going to get f of x is equal to negative 2 x minus 3/2 squared plus 13 over 2. That was a little bit involved, so you have to make sure you practice your completing the square. Our vertex, based off of this, is positive 3/2, positive 13/2. I'm going to go over to our graph. I'm going to put that on our graph. Positive 3/2 is 1.5. It's sort of hard to get there, but you can see 1.5. And 13 over 2 is 6.5. So you can have your vertex right there. Now my graph is going to be pointing upside down. We do know that the y-intercept, if I plugged in 0 for all of this, my y-intercept would be 2. And so that would also give me a point right here. And so there we go. We graphed the function. The next page in our notes just has a table with some properties listed, and we're going to apply our knowledge of quadratic functions and describe it using the properties listed on this page. And I have at the top, I've written in the equation of the quadratic function in vertex form, and then we have two different graphs showing one where the a is positive and one where the a is negative, and we'll talk about what changes that makes. For the vertex, for both of them, the a has no effect on the vertex. It's always going to be hk. For the axis of symmetry, you have to make sure that the axis is an equation of a line. You can't just give a value. You have to give the equation of the line. And it's a vertical line, so it's going to be x equals, and the line is going to be at x equals h. Notice that h is from the vertex. Now the concavity, because the a is positive, this one's going to be concave up, while when a is negative, it's going to be concave down. When it's concave up, it has a low point down at the valley, and so that actually has a minimum. When your a is positive, you have a minimum, but when a is negative, you have a maximum. Because you can see those high and low points. Our x-intercepts cannot be found in this manner very well, so I'm going to skip that for right now. We're going to go to y-intercepts. You're going to plug in x equals 0. So don't forget that your y-intercept is when you're finding f of 0. Now, you can plug it into this equation, but if you have it in general form, let me write that over here. If I do have my equation in ax squared plus bx plus c, and you plug in x equals 0, then my y-intercept is just c. Notice because those first two terms will cancel out. Now we have some interesting concepts coming up. The domain for parabolas and for quadratics, they are all real numbers. You can write that in words or in interval notation from negative infinity to positive infinity. And then the range, it depends on if it's facing up or down. So I just want to look over here. The range describes the y values. We have a minimum value. Our minimum value is our k value. And so we're going to say it starts at k and it goes all the way to infinity. While if it's concave down, you're going to start at negative infinity and go all the way to k. And the k is going to be the endpoint because that's where the vertex is, but it depends on which way the graph is facing, so that we know if the k is the first point or the last point on it. You have to make sure that you understand that. For our x-intercepts, I want to go back to that line real quick. For our x-intercepts, you want to find out when it's equal to 0, not when x is 0, but when f of x is equal to 0. And that's harder to do in vertex form. It's much easier to do in general form. And you would set your quadratic equal to 0 and then you solve for those intercepts. So we're not going to do that right here. There's no generic formula for it. You would want to solve by factoring or any of those other methods we talked about before. And I just want to go back real quick to our maximum and minimum values. I wrote that it has minimums and maximums, but I forgot to tell you what values those are going to be at. And the value is k. K is our y value. Every time we talk about max or mins, we want to give the y values. So I could say, that the minimum is y equals k, or just k, and it happens at x equals h. So you don't have to say the at. It's important that you know, though, that the preposition is it is k at h. Another way that I like to write this, just to be extra clear, I say it is y equals k at x equals h. So I know which values is which. But once again, my maximum is a value happening at another value. So you would take that vertex and you split it up into two pieces. The minimum and the maximum talk about specifically the y value. How high does it go or how low does it go? Then you can tell me where on the x-axis does that minimum lie. So it is a y value at an x value. Alright, we're going to use these properties that we just talked about to graph this function f of x is equal to 3x squared plus 3x minus 2. And before we do that, I do want to take that function and rewrite it in vertex form. So once again, getting some practice in with this, we're going to move our c term over to the other side. So we're going to add it. And then we're going to factor that 3 out of the remaining terms. Leave some space. Just to think about it, this coefficient, the first coefficient should be 1. The second coefficient happens to be 1 also. We're going to take that, divide it by 2. That's going to be our term, and we're going to square it to add it to both sides. So I'm going to add 1/4 here. And on this side, I'm going to add 3 times 1/4, remembering that I have to multiply it by that coefficient here in the front. And simplifying that, I get f of x plus 2 plus 3/4 is equal to 3 times x squared plus x plus 1/4. and I'm going to get f of x, and ooh, I have some numbers that I want to add up, so I'm going to say 2 is the same as 8 over 4 plus 3 over 4. And so notice how I do some of my work on the side, because I don't want to have to write my equations multiple times, but I want my equation to always be equivalent to the equation above it. So I'm going to factor this one, and that I'm going to pull this 1/2 that we have from before, and we will get x plus 1/2 squared. And then subtracting the 11 over 4 from both sides, we're going to get 3x plus 1/2 squared minus 11 over 4. Alright, so I'm going to take that and write that up here next to my function, because we're going to reference that for a lot of our work. Alright, and then I'm going to erase all the work I just did. Now don't go about erasing your work, I'm just doing that to give myself more space to write on. But on your paper you should leave your work there so I can see it. Alright, looking at these two functions, they're exactly the same function, just written in different forms. I'm going to answer all the stuff that I can answer with it written in vertex form in blue. It's going to be concave up because my coefficient was a positive 3. The vertex is going to be negative 1/2, negative 11/4. I can pull my axis of symmetry from this graph. That's always going to be an equation, which is x is equal to. And then we also can say that the domain is all real numbers. And then the range is going to be from the y values. So let's just do a quick sketch. When you're looking at the graph, the y values go up. So we have the vertex, which is going to be hk, and we're going to be going up from k. In this equation, our k is 11 negative 4, negative 11 over 4. In this equation, our k is negative 11 over 4, so that's going to be our lowest point, and then we're going to go all the way up to infinity. And then we can look at our increasing intervals. We have two intervals. I'm putting them here. It depends on if it's concave up or down, but you want to say for the left side, we're actually going to be looking at this interval because it's decreasing. I want to say that it goes from negative infinity to h. That's the decreasing interval. My h value is negative 1/2. And then over on this side, it is increasing in value. So I'm going to say from h to positive infinity, that's going to be that interval. And h, once again, is negative 1/2. And then my local max and my local min, I do have a local min. That min, it happens at or my minimum is my k at my h. So in this one, I'd say my minimum is negative 11 over 4 at x equals negative 1/2. Now you don't have to give the at information. The only part that's really important is this, my minimum is. So you have to make sure that you remember which value you're pulling, the h or the k value. Alright, I'm going to erase my work again to give myself some space to solve for my x and my y intercepts. The y-intercept is a little bit easier to do because to find my y-intercept, is a little bit easier to do because I'm just plugging in 0 into my first function, and I'm going to get 0 plus 0 minus 2. So my y-intercept is 0, negative 2. my x-intercepts is a little bit more involved. I'm going to, instead of plugging in 0, set my equation equal to 0. And this is something that cannot be solved with factoring, so I'm going to solve it using the quadratic formula. I'm going to say x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to simplify that. And after I simplify that, I can't simplify that anymore. That radical cannot be simplified. I could maybe write it as negative 1/2 plus or minus radical 33 over 6, but that doesn't really give me those values. Using a calculator, I can figure out that one of my x-intercepts is negative 1.457. And my other one is 0.457. Now, I really don't want you to give me my answers in decimal approximation. I would prefer your answers are written in this format. So when you're talking about x-intercepts, you're going to say negative 1/2 plus or minus radical 33 over 6. Why did I write them in decimal approximations? Just so that I can graph it, and I don't know where those points are if I leave in radical form. But if I say, oh, negative 1.4, then I can sort of go to that spot on the map, on the graph. And we graphed this function after we figured out all the different properties. Notice that the vertex is right here, and that is negative 1/2 and negative 11 over 4 written in decimal form. We can see our y-intercept and our two x-intercepts, and that matches all the information that we have up here. You can see that it's concave up, it has a minimum. We do have an axis of symmetry. That would have been roughly right here. I'm having trouble drawing it correctly. But all of those different things that we have in the properties are showing in the graph that we have below. Number 4 asks us to determine the quadratic function whose graph is given. We have some information in the graph. So we do have the vertex, which leads us to think that we can use the vertex form of the equation. Now the vertex is hk, and you're going to take that and plug it in, but we still have to figure out our a. We're most of the way there. Now we want to plug in the other value that we know. This y-intercept gives me x equals 0 and f of 0 equals 5. So I'm going to replace the x with 0 and the f of 0 with 5 in my equation. So now basically, let me do it in 2 steps. I'm replacing my x with 0, and I'm replacing the f of 0 with 5. And let's just go ahead and solve this. I get positive 4. Subtracting 1 from both sides gives me 4 is equal to 4a. So a is 1. That's awesome. So my equation is f of x is equal to 1 x minus 2 squared plus 1. And that first one is optional because it's being multiplied. So you can just say x minus 2 squared plus 1. Now we arrive at the last question in this section, and I just want you to see that the equation is fairly complicated, and I don't expect you to do this by hand. I expect you to use some technology, either your graphing calculator, like we will practice in class together, or with using some graphing technology like Desmos.com, which is what I'm going to be showing you in this lecture video. The question talks about a projectile being fired and the location. The height of the projectile is modeled by this equation that's given to us. And x is the horizontal distance of the projectile from the firing point. So looking at part A, it says, at what horizontal distance from the firing point is the height of the projectile? Let's bring in the graph. So looking at this graph that I pulled from Desmos.com, I'm able to see that I have two x-intercepts, and I have some type of symmetry going on. I can imagine that the axis of symmetry is going to be halfway in between those. So you can use your calculator to figure that out. And I get 156.25. So it's going to be 156.25, and what's my units? Oh, over here I can see that it's in feet, so I'm going to say feet. The height of the projectile has a maximum over here. The distance, that's 156.25 feet from when we started. The next question asks us to find the maximum height. So not the distance on the x, but the height of the y. So we want to find the maximum height of the projectile. Once again, I'm going to refer to my graph. And I just pulled my graph from Desmos again, and all I did was find that midpoint. Now this is my vertex right here. And this was the distance from the horizontal distance from firing point, and then this is the maximum. So the maximum height of the projectile is 78.125 feet. Making sure we always use units. We can use the same graph to answer part C, which asks, at what horizontal distance from the firing point will the projectile strike the ground? It strikes the ground right here at this point when the height is 0. And so we know that from the firing point, that's going to be a distance of 312.5 feet. And part D asks us to graph the function, which we already did, and we even used that domain of 0 to 350. And so we actually use the graphing utility to help us get those results, so we don't have to verify. Part E says, when the height of the projectile is 50 feet above the ground, how far has it traveled horizontally? So to answer this question, I want to graph another graph. The height is always 50 feet. And then I want to intersect these two graphs and see how far it's traveled. So let me pull up the graph. So looking at this graph, we have the line at 50 graphed for us. We have the height, the y values are 50, and it intersects the graph twice. So when it says when the height of the projectile is 50 feet above the ground, how far has it traveled horizontally? It has either traveled 62.5 feet if it's on its way up, or it's also traveled 250 feet if it's gone all the way up and it's coming back down. And so we've answered all the parts of the graph, all the parts of the equation using the graph to help us find out a lot of things. You have to be very comfortable with the graph, understanding that H value was the Y value here in the graphs, and that the X value was the distance horizontally. And if you understand all those pieces, then just looking at the graph, you should be able to figure out the answers to all of these questions. And that is section 4.3.